So welcome everybody again to this IAU G2 online conference series. This is about massive stars, and this is going to be the last seminar of the year. So I hope you've been enjoying this first year of seminars and to see many of you also the next year. Today we have as invited speaker Alex Gormaz-Matamala. He did his master studies at the Universidad Concepción and then the PhD in Universidad de Valparaíso in Chile under the supervision of Michel Curie. And his PhD thesis was focused on the calculation of self-consistent solution between line-driven acceleration and wind hydrodynamics for massive stars. During his doctoral study, he also did some internships at the University of Pittsburgh, collaborating with John Hillier, learning how to use CMFGen, and then also Trinity College in Dublin, together with Jose Gros, learning about the use of GenEC. And he was also part of the POEMS project led by Nicolaous. Then once he finished the PhD, he continued as postdoc in the Universidad Adolfo Ibáñez, also in Chile, working on massive stars at the Gallatin Center. And after that, he moved to where he is now, to Nicolaous Copernicus Astronomical Center in Warsaw, in Poland. And now he's working with Professor Chris Belsinski. So let's see what you want to tell us today. We are really looking forward to see your results, and whenever you want, Alex, you are more than welcome.
Okay, well, thank you, Sergio, for the invitation and the introduction, and thanks all of you for attending. I will present new results and preliminary results of future studies that we are doing. And the title of my presentation is Impact of Adopting Hydrodynamically Consistent Winds for on Stellar Evolution. Okay, the first part is about what do we mean when we talk about self-consistency in winds in massive stars. So first of all, massive stars in the universe, why they are interesting to study. Massive stars are stars born with 10 or more solar masses. They are important and interesting topic of study because they enrich the interstellar medium with helium and CNO elements. And also they are progenitors of compact objects such as neutron stars and black holes, which are responsible of create gravitational wave events. And as you might know, in the last years, thanks to the detections such as LIGO or Virgo, new sources of gravitational waves and doubly compact objects has been detected. And therefore, it's important to know how these structures are formed. And in this case, understand the evolution of massive stars is key. And in order to understand the evolution of massive stars, we need to understand the most important feature that they have, besides being the brightest and the hottest stars in the universe. They also are characterized by powerful, strong stellar winds. These stellar winds are so strong, we also name it line-driven winds, because the process about how these winds gain so much moment to take off a huge part of the outer envelope of the star is because of the radiation coming from the photosphere is absorbed and posteriorly emitted by elements present in the wind. So this is why the process is called line-driven. Has some peculiarities, such the wind needs to be dense enough in order to share this gaining of momentum by individual ions to the entire wind structure. So that's why, for example, we have it for massive stars with 20 solar masses, but you don't find line-driven winds for the sun, for example, because the wind of the sun is not so dense. To theoretically understand parametricize stellar winds, we use two parameters. One is the terminal velocity, which is the velocity reached by the wind particles at the infinite, and more importantly for us, the mass loss rate, which is the rate about how much mass is lost in the outer envelopes by the stars. At the same time, we mentioned the hydrodynamics of the wind. Every time that we will say about mention something about hydrodynamics, we meant the density and the velocity profiles of the wind, because they change through larger distances. And these two elements are, of course, connected because there is a mass continuity that needs to be satisfied. So that's why these elements are intimately connected. No, I'm not gonna put too many details in the questions, just a brief introduction showing that those are the the equations that we need to solve in order to calculate both the wind hydrodynamics and also the mass loss. In particular, this is the equation of motion, of momentum. And this element is important because it's the line acceleration. That means the acceleration produced by this process of absorption and re-emission. And this is not a simple problem because this G line, it's also dependent on the radius, the density, and the velocity gradient. So this is not a straightforward problem. But we have developed different strategies in order to find solutions for the wind. In particular, we will mention two, the MCAK prescription and the Lambert procedure. For the CAK prescription, we have to mention the so-called line force parameters, which consist in the previous term of the line acceleration. We just parametricized using three parameters, like K, alpha, and delta, which can be used to recreate the hydrodynamics of the wind. This is the velocity profile and density profile. And more importantly, this parameterization, this velocity profile and density profiles can recreate line profiles such as H alpha, as you can see here, in a different way that normally all prescriptions for wind velocities, such as the famous beta law, is assumed. Normally for velocity profiles, it's assumed an exponent called beta, and we call to that beta law, but you can see that when we use like the line force parameters, the velocity profile, the density profile, and the line profiles are totally different. So there is a very recent paper about showing the effects and the differences with beta law made by Roberto Venero et al. And also strongly recommend you to have a look on the review that Curea and Araya also both from this year. But in our case, my case particular, we did the extra step of not only give some K alpha and delta, but also calculate them. And since we do this, we calculate K alpha and delta based on this function that needs the wind hydrodynamics, because we need the density and the velocity profile to solve this relationship, this sum of the individual lines that contributes to the wind. And at the same time, we use K alpha and delta to solve the previous equation of motion that we show using the code ILWIN. So we repeat iteratively this process until we get a final solution. And when we get a solution that is converged, we obtain a final mass loss and final velocity profile, expressed as a terminal velocity in this case. And that is why we call what we call the self-consistent solution, because the line acceleration for one side and the hydrodynamics are coherent one with each other. And based on that, the mass loss that is obtained, it's unique given a particular set of stellar parameters. So if you have one temperature, one specific radius, and one specific rotation, a particular abundance, you can only obtain one value of mass loss. So this has advantage, for example, for spectral fitting, as we will see later, but it's important to know that that is what we call later the self-consistent mass loss rate. In parallel, we also develop a new strategy to calculate wind velocity profiles. In this case, we make the solution analytically, and the G line in this case is calculated by more sophisticated codes of radiative transfer, such as CMFGen. And in this case, we obtain a more complex solution instead of not using previous assumptions that we use for the MCAK prescription. However, because of the same, the computational time used for this Lambert procedure, it's higher, so it has not been possible to extend it for different range of velocity, effective temperatures, or different surface gravities. So because of this reason, we will focus for here in the mass loss given by the CAK prescription. About the CAK prescription that we previously mentioned, besides these differences, the results between the mass loss constrained by the Lambert procedure and the mass loss calculated by CAK prescription are fairly enough, close each other. In particular, we found that our values are lower than the values for mass loss that normally has been used for stellar evolution. In particular, these orange points, which are the so-called Fink's formula, which has been the mass loss recipe for the last 20 years. But also, it's in a middle point with other WINS prescriptions that made by Kritichka and Kubat. So our MCAS prescription gives values in that middle, being close to Kritichka and Kubat when we are at the beginning of the main sequence. This should be actually a spectral luminosity class 5. So, and at the same time, as we mentioned, the MCAS prescription not only gives a new value for mass loss rate, but also a value for the velocity profile and a density profile. So we can use this to fit different spectra. We made this, by the moment it's still constrained for the optical range, and the next step is to extend it for the UV, but it's an important step forward. So, so that is the base of our new WINS prescription, the self-consistent mass loss rates. And now the next step is to incorporate this new value in developing new evolution models. Just to put again the same that we said previously in terms of simple to easy to implement formula, we fitted this formula that looks a little bit intricated, but has some important advantage, such as a not so constant relationship between the mass loss and the metallicity, because normally people have assumed that mass loss, the relationship between mass loss and metallicity, it follows a power law, but assuming the exponent as a constant. But more recent studies show that for more massive cases, this relationship between mass loss and metallicity should be less steep, which is also consistent with other studies such as Kritichka and Kubat, even when they put their fit in terms of luminosity, whereas we put it in terms of mass, the physical reason behind is the same, that for more luminous, for more massive, you have more continuum, so the effect of lines is less relevant. And okay, so this now let's go to evolution models. Evolution codes such as the Geneva evolution code, which is the code that I am currently using, needs a recipe for mass loss given the position in the HR diagram, which is of course related with the spectroscopic conditions at every part of HR diagram. So during the evolution, sorry. This has been normally the set of formulae that has been used in the last, I think, 20 years, using the so-called Fink's formula for the most part of the massive stars during the main sequence and a little bit beyond. Well, or formula for the Jagger for less massive stars, and For the case of Wolf-Rayet, a mix between Grafener and Hamann and Nugis and Lammers. The new stellar winds that we mentioned previously, based on cell-consistent calculations, and also in the another studies such as Björklund, for example, Kitishka and Kubat, are based for the main sequence stage. Or because of that, we call this part the optically thin winds, because it's the moment when the wind is thin enough to distinguish between the photosphere and the wind of the star. For other more evolved stages, such as Wolf-Rayet, this is not easy to do. But at least in the beginning of the life of the star, during the main sequence, we know that the wind needs to be revisited by 2 or 3 times, depends on the formula. And because of the masses is very important, this change makes an important effect. These effects are summarized here, but we will see in details in plots later. So, of course, if we use lower mass loss in stellar evolution, the stars will keep more mass through their evolution. It's an obvious condition, but that also means that the star will be larger in size, and because of that, it will be more brighter. But besides, if we could take into account the rotation of the star, the effects are more intricated, as we will see later, and also, let's say, more interesting. So for non-rotating models, this is the situation that we observe. Hereafter, important to mention that all the plots made by new winds will be always with solid lines. And whereas plots made with old winds, we're using Finn's formula mostly, we will be with dashed lines. In this case, we are comparing non-rotating models for the galactic metallicity, LMC metallicity, SMC metallicity. And we took these models for, well, in the case of galactic metallicity, from the work of Sylvia, the work of Patrick Egenberger, and the work of Cyril Georgi. However, what is important to just to reinforce what I said previously is that this effect of that lower mass loss make the star evolving slightly brighter in the HR diagram is just relevant for solar metal when the metallicity is high enough and when also the mass is high enough. You can see that in these cases the difference is meaningless. However, when we take rotation into account, the situation is more interesting, because in this case we have a rotational mix inside, and the inner structure of the abundance from the core to the surface are more interesting. In particular, lower winds are removing first of all, are removing less mass, so removing less outer envelopes. So the star keeps some inhomogeneous structure for a longer period, which makes the star evolve a little bit more redwards compared with old models. By the way, these models are just constrained to the main sequence, because it's the part that we need to explore in this moment. So that's why you see that they are not complete. But it's because we are focusing in main sequence. And again, this effect is more prominent for the cases, for the most massive cases, and the effect is a little bit different for the low masses. By low, I mean 25, and lower metallicities as well. That the track are all mostly the same, but you can see that the end of the main sequence is a little bit at larger metallicity. But we will explore this particular case later. And talking about the difference in the losing of not only mass but also angular momentum, that creates that adopting new winds make the star keeps a faster rotation for a longer period. Something that we can say, we can call it slower breaking, because of course the star starts with some initial rotation and ends close to 0 at the end of main sequence. But the way how we go to 0, it's totally different. It's more abrupt when the winds are stronger. With weaker winds, this situation is more moderate until before the final end. And about the inner structures, we compare here the case of the star with 70, born with 70 solar masses at the end of the main sequence. And when we talk about homogeneity, the level of homogeneity, it's shown in this plot. It's like for the old model, you see that the difference between, let's say, abundance in oxygen from the core to the surface is lower. The difference is smaller compared than the model when we have when we adopt weaker winds. See, in this case, the star is more heterogeneous when we adopt weaker winds because the removal of the outer envelopes are lower. This difference, however, is not so important for the case when the masses are lower. In this case, you can see that there are not many differences in the inner structure, but we will see later that for masses in the range of 20, 25, and even lower metallicities, there is another effect, an indirect effect coming from the weaker winds. So just a brief summary. We don't need to look at all the columns, but it's important to mention the difference in the chemical abundance. So you can see that weaker winds, because of the same condition that we discovered previously, that we are removing less of the outer envelopes. At the end of the main sequence, the chemical evolution is a little bit smaller. So the mass fraction of helium is always smaller, the same with the N over C and N over O ratios. The only difference, the only exception is this last model with 25 solar masses and LMC metallicity, where we observe that the mass fraction of helium and these ratios are larger. This is because the absolute value of mass loss is not too much, and in this case, the losing of the important is not how much mass do we lose, because you can see there are not many differences, but what matters is the difference in the losing of angular momentum, and that keep the star rotating for a longer period, and this extend the life of the main sequence. But even when this is the exception in this case, but we will see later that it becomes a rule for lower metallicities. But we need to also contrast these results with some observational diagnostics. And in this case, we selected the survey developed by Gonzalo Gago in 2020 and 2022 as part of a Jacob project, if I'm correct. In particular, for this image, we recreated the plot of the rotational velocity as a function of the effective temperature. Something that is remarked by Olga et al. Is that not either the evolution models of Geneva or models of Brod that I included here, but just for a matter of clarity in the plot, not any both of them they could fit the expected sample shown in this plot. On the contrary, the good news for us is that the self-consistent, the evolution adopting weaker winds, we match better this over-density region of the plot. Why? Because we start all of these models with the same rotational velocity, but as we saw in the previous panels, first of all, we keep this higher rotation for a longer period at the same time that the tracks, the new evolution tracks moves redwards compared with old tracks. So this is why we have this horizontal movement before the final drop off in terms of the rotational velocity at almost constant effective temperature. So we can see that this over-density of the majority of the samples shown here is easily encircled by the model of 25 or even the model with 70 solar masses. And also the new evolution models easily explain why we have a lack of stars in this region with high rotational velocities, but also high effective temperatures as well. So this is a very important plot for us because it shows that adopting new winds are better to explain the observational constraint diagnostics made for stars, at least in the Milky Way. Still is a survey of only 300 stars. There are many more massive stars in the Milky Way, but it still is an encouraging result for us to rely in what we are observing in these new plots. So based on that, the highlights of this part is that self-consistent stellar winds provide lower mass loss or weaker mass loss, as we can say, that we have this not so constant relationship for the mass loss and metallicity dependency. Weaker winds may the star retain more mass and more angular momentum through the evolution, and the rotational velocities predicted by our models shows a better agreement with observational diagnostics. So this is the final remark that we do with the work we have done until now. So what is next is what are the rest of the impact, which other situations we can explore and we can conclude. In this case, for this situation, we separate in two main extensions. One is extension towards lower metallicities. In this case, we will explore rotation for SMC metallicities, and then we will see very massive stars. So for this case, it's basically the extension of the previous study, but in this case for LMC small Magellanic Cloud metallicities. What is shown here is the same effects that we saw previously, but in this case, you can see that the tracks are more similar for a larger range of masses in the lower part. And again, we see an extension of the point when the main sequence ends. And this is consistent with this other plot when we see that the age of the models, the moment when we reach to the end of the main sequence represented by this black circle, it's extended in time compared with old models. In this part, this abrupt vertical line corresponds to the increase in radius because of the closing the Hertzsprung gap. And for the less massive models, this situation is the lifetime of the mass loss is extended. This happens because the star keeps start rotating fast because of we are losing less angular momentum. We keep the rotation faster for a longer period, and for the case of the less massive cases, this rotation is even strong, even close to the end of the main sequence. And because of that, the mixing is also strong, and the hydrogen abundance in the core is refueled by the outer layers because of the mix. And this explains why the lifetime in the main sequence is extended. And because the lifetime in the main sequence is extended, the star has more time also to continue mixing in the surface. And this creates this plot of the right as well when we show the N/C ratio in terms of the age, and the black cross represents the ends of the main sequence. Again, we are just focusing the main sequence, at least in this part. So for the more massive cases with 85 and 60, because the mass loss is still plays a more direct role. Since we are losing less envelope, we have a lower chemical evolution, but for 2025, 32, the effect is the opposite, because the loss in the envelope is not so relevant, and the extension of the main sequence lifetime becomes more relevant. So in this case, we see that the N/C ratio is stronger when we have weaker ones. And this is also where was the same that we observed for the model weight 25 and solar masses and LMC metallicity. What is also in construction we are also building is trying to explain the same situation that we discussed previously, contrasted with some observational values, observational diagnostics. In this case, we are using the studies of massive stars in the SMC made by Jean-Claude in 2013 and 2021 for main sequence stars and also for giants and supergiants. Unfortunately, because of SMC, it's a little bit far away compared with the Milky Way. The uncertainties are larger in this case, so we are still trying to figure out about which conclusions which things can we conclude by comparing the new results on stellar evolution models and observational diagnostics. But anyhow, this is important. This is important because the idea is extended this for thinking in projects such as X-Shooter, which should improve the measurements of the spectral measurements of stars in distant galaxies. So in the meantime, we need to continue developing evolution studies. And another table, but what just important to show here, it's the final masses. Again, because the winds are weaker, we observe the new models of adopting new winds. The final mass is always larger, but we see that this effect is contrasted during the sorry, here there was a mistyping. This should be end of helium core burning. It's contrasted, and in this case we have smaller masses at the end of the helium core burning in this case. And the point is, even when we are using for this period the old recipes that had been used before, we only upgraded our winds for the main sequence stage. But even when we are using the same winds in this part, we are starting from different points in the HR diagram. In particular for this star, we start for these stars, we start in a more luminous point in the HR, and that implies a slightly higher mass loss. And this is what compensates the resulting mass loss and resulting final masses. And the result for the abundance is the same that we described previously in the previous project. So not so concluding remarks, because it's still work in progress, is that in this case we have an impact direct when the mass loss is important enough, and we need to take care about the removal of outer envelopes, and an indirect effect when it's more important, the extension of the lifetime and the rotational mixing, because of the weaker winds make the star lose less angular momentum. And as we mentioned, the idea is continue extending this even for, we hope, even smaller metallicities to complement the studies in massive stars as done by X-shooting Ulysses. And the final part is the implications that we have for, in this case, very massive stars and mass remnants. What is a very massive star? We mentioned at the beginning that a massive star is a star with 10 solar masses, born with 10 or more solar masses. In this case, a very massive star is born with around 100. I mean, the limits are still, of course, very liquid, but 100 is a good number to take into account. If massive star had strong stellar winds, very massive star has very strong stellar winds. Because of this situation, very massive stars enters into the wall riot stage, showing strong emission lines and everything, even when they are still in the main sequence. Those are the so-called WNH stars, or wall riot in asteroids, as we call it previously. And taking this into account, evolution codes normally set one parameter to consider the switch between, if we are using mass lobes for OB type stars, the so-called optically thin winds, or we will use mass laws adopted for wall-rayet stars, optically thick winds. Normally, this criteria has been the hydrogen abundance in the surface, 0.3 or 0.4. However, there are spectroscopical evidence of that you can find even WNH stars or stars showing features of being a WNH candidate, even when with larger values of hydrogen abundance in the surface. So what we propose is to find another transition point between the thin winds and the thick winds. This is not totally new, however, there have been studies that has been focused in trying to evaluate the transition between thin and thick winds based on the proximity to the Eddington factor, being the Eddington factor defined as here. We already know that when Eddington factor is equal to 1, it cannot be a star because it's radiation totally disrupted star. But even when it's below 1, but close to 1, we can have interesting effects. In this case, what this author found is that the relationship between the mass loss and the gamma becomes steeper when they approach to 1. And this, of course, means that for lower gamma, we are talking about optically thin winds, as we described before. For higher gamma, we're talking about optically thick winds. So that could set the transition between OB type stars to wall-rayet in terms of the wind conditions. And some other studies have been recently also for Sabah et al. Also trying to find this transition point, but doing this in a smooth way. So the switch in this case is there is no any abrupt jump in the mass loss. And this gamma A switch is it's based on this. However, they still use enhanced winds for the optically thin part. And what we are interested, or I am interested at least, is how do we compatibilize, or how do we merge optically thin part winds that we already know that they are 2-3 times lower than Fink's formula, with optically thick winds, the most upgraded recipes that we can find now in the literature. So in order to do that, we came back to the CIK theory that we mentioned that from the CIK prescription. There is studies such as made by Joachim Westerlener analyzing how is the relationship between mass loss and the gamma Eddington factor for the 2 cases extreme, when gamma is very close to 1 and when gamma is very close to 0. So the 2 extremes. And he found that the both extremes merge in some gamma value that in this case is set it as a gamma trans for transition, which are shown here in this table, and those whose values are around 0.46 and 0.48. The same. This is interesting for us because in our self-consistent wind models that we developed, we also calculated alpha and delta, and the result for the alpha that we obtained was also in this range. So based on this, we decided to run new evolution models, but replacing the former condition for the mass fraction at the 30% for reaching gamma equals 0.5. So the star, if the star has a gamma Eddington factor below this 0.5, we will use optically thin winds valid for OB type stars. And for that, we implement and adopting the recipe that we saw previously. For optically thick winds, at least in the first period, we make the distinguish between H-rich and H-poor. For H-rich, we use the formula of Westerlener, and for H-poor, we use the hydrodynamically consistent formula from Sander and Fink of 2020. Comparison between these new formulations and the new formulations can be seen here in order to have an estimation about how are different. However, it's important to mention that the mass loss and the luminosity, they are not strictly coherent or related in all of these formulations. But this is a good way to see at the same point in the HR diagram which mass loss should be stronger than other ones. We implemented, because for a matter of time, we implemented this not in, I mean, we are running models in Geneva code for this, but we made it by the moment for MESA. Well, for Geneva, we obtained this. This is a comparison with all tracks made by Yusuf et al. For a star with 200 solar masses. What is interesting for us is since our winds mass loss are lower, we predict or we found that the end of the main sequence is still at very high luminosity compared with all models that they assume that they found that the mass loss is strong enough since the beginning to quickly have a drop in the luminosity. So all models finish the end of the main sequence of hydrogen core burning here, and we found it here. It's an important difference in luminosity, and because of that, when we start the helium core burning, the differences in luminosity makes that the difference in mass loss rate is also very strong. In this case, this is the comparison of mass loss through the hydrogen core burning. So that's why we put it in terms of the hydrogen core. And this is during the helium core burning. So that's why we put it. And you can see that in this case, the difference is 10 times. And because of that, we have the suddenly drop during the helium core burning. And even when we finish at almost the same end, the difference between hydrogen core and helium core are important. We adapted this for MESA models as well. Also changing the overshooting and some other evolutionary parameters that are important. Even with MESA, we found a similar behavior. And we use these new results to send a plot of random plot of different initial masses and trying to calculate the final mass, because the final mass is important to know the mass of compact objects such as black holes and neutron stars. And in order to do that, we need to upgrade the mass loss recipes through the evolution of these stars. So in this case, we are showing, well, 20, 30, 60, 180, or 300. Depending on the condition that we said previously, they will have thin winds, thick winds, and so on. And this gray part, it represents the final mass, as a ratio of the initial mass. However, this is easier to observe in this plot, which shows the final mass, which is supposed to be close to the mass of the expected black hole if we don't consider supernova conditions. And it's an interesting result because previous studies of Bavera, they found that the top of the most massive black holes that can be in the galaxy will be around 35, 36, starting from a start of 17. In our case, we don't find so huge mass for a black hole, but we also have this very drop. We also find that the maximum black hole shouldn't be found for the very massive stars, but more for this region. Still, these new models that we are seeing here are done with a rotation of 0.4 in as a fraction of the critical velocity, and with a upgraded overshooting and some other conditions such as Telos Brut, that just to don't put too many things I barely mentioned, but this is the new function for final masses of massive stars that we found, that we just submitted previously a few weeks ago. So just to summarize everything, we have new evolution tracks for different analyses are important for very massive stars, and those are the results when we upgrade mass loss, not only for the main sequence part, but also for world-wide stages. Something that I didn't mention, in order to synthesize as much as possible, we can also explore the massive stars in the galactic center. That is also something that we are doing. We changed the transition point for very massive stars from the previous, based on the hydrogen mass fraction to gamma emission factor. And because of this, we obtained new values for Riemann masses at the end of stellar evolution. So this has been all. Thanks all for your attention.
Thank you very much, Alex. Very interesting topic and ideas and results. So now it's time for questions. If anyone has any question here, please tell it in the chat or... Gloria, please go ahead whenever you want.
Yes, thank you for the very interesting talk. I was wondering, do you consider the stars rotating in uniform rotation throughout their evolutionary lifetime, or is differential rotation considered to produce the tracks?
We assume, when we talk about rotation, we assume standard rotation of being 40% of the critical velocity. We use the omega 0 equal omega equals 0.4. So, I mean, it's under debate. If we know that not all the stars are born with the same rotation, but it's we need to somehow uniform this. So we still keep the 0.4 as previous models.
Okay, thank you.
Fabrice?
Yes, thank you for this very nice talk. I had a question about the first part where you show your new models with the reduced mass loss rate. You probably know that when we plot the abundances versus rotation, I think you showed that at some point. It was for the SMC, but you know that there are a fraction of stars that are, yes, this kind of plots. When there are a fraction of stars that are not so rotating rather slowly and but are already enriched. One of the solutions to this is to have models that break more easily, which is one of the problems of the bone models. For instance, they keep too much angular momentum, so they they rotate too fast for a given abundance. But so if I understand, in your models, you also keep more angular momentum. So you would tend to stay at higher rotation for a given enrichment. So that would actually exacerbate the problem, right?
Mm-hmm. Yeah, that's a good point. It's like, I mean, when we made the comparison for in the Milky Way with the survey of Olgado, the situation was very promising because it's like, okay, our result was in the middle between what was predicted by the models of Broad, and that they were, as you say, they lose very low angular momentum, and the models of Geneva adopting higher winds, which predict a very high decreasing. Unfortunately, for the case of SMC, we are still, I mean, we keep, of course, the higher rotational velocities as shown here. So in that sense, it doesn't look very promising compared with the plots that are shown in these two surveys. Just for a matter of clarity, I deleted some stars of your surveys because that they were located here, and there was not even old or new tracks to fit them. So yeah, that is something to think about, especially for SMC stars.
Okay, thank you.
Any other question here? Yes, Ina, please go ahead whenever you want.
Yes, can you hear me?
Yes.
Yes.
Yeah, thanks so much. it's about this plot that you're showing now. I'm not very optimistic about the observations. Do you have any comment to add if these stars are really single star or they are in a binary system?
It's a good point. To be honest, I don't have sure which percentage of these ones are single or binary. This part we just made it, I think, 2 weeks ago, so I didn't have time to contrast that part. So
Okay, thanks then.
Yeah, but it's clear that we need to also take into account the binary channel, not to interpret all these diagrams.
yeah, that's right. It's like yeah, it's a. I mean, it's a. Yeah, this is. I mean, this part is the part of the observational diagnostics, and yeah, we need to compare with something. But as I said, this part is still in progress. Binarity needs to be, of course, considered, but what is still worth to mention is that the result we showed for SMC, it's an extension of the result that we were previously showing. We were previously observing for galactic stars and also for LMC stars. So yeah, and also we would be nice also to have I mean new results for extended samples to make better comparisons.
Okay, any other question here? No, so I have
there's a comment of Fabrice.
in the samples of Puret, there are no SB1s or SB2s.
Okay, so those are singles.
Okay, good to know. So from the first part of the talk, when you're talking about these self-consistent winds computations, so I'm curious what you will consider are the weak points of these computations. I mean, what are the fine-tuning parameters or the tricky points that you have to consider when you do these computations? You do any approximation or this is completely self-consistent?
Yeah, it's well, in terms of the parameterization, MCNK prescription has the advantage of we can get models fast because we are taking a lot of assumptions, well, some important assumptions. It's like we're still in CAK theory, so we rely in the conditions of CAK theory, such as the Sobolev approximation, for example, for instance. On the contrary, calculation, on the contrary, Lambert procedure, for example, it's more complete because the solution is analytically without any parameterization, and the line acceleration is formally calculated by radiative transfer, in this case, using Simmel-Jen. However, so and another important point is we, for the MCIK prescription, we are assuming that the linear force parameters that we mentioned, they are supposed to be constant through the wind, something that some authors have claimed that is not the case, at least not for all range of temperatures and gravities. Because of that, we constrain this solution for a region in terms of surface gravity and terminal velocities where the assumption of line force parameters being constant, it's reliable. And I didn't put it here, but it's valid for stars with log G over 3.4. So stars that are not blue supergiants or something. So that is part of the weakness, as you mentioned, that because of that we also strengthen the constraint of the range of validity.
Okay, thanks. Any other last question here? If not, let me thank you again, Alex, for this very interesting talk and accepting our invitation. So hope to see many of you next year also in the seminar. So it's working very nicely. So I hope this will continue with more new young researchers as speakers. So thank you very much, everybody, for joining.
Thank you so much, Sergio, for the invitation.